Welcome, everyone. Today, we're going to explore one of the most fascinating and counterintuitive phenomena in deep learning, something called grokking. Watch what happens here. The training loss drops to near zero almost immediately. The model has perfectly memorized the training data. According to traditional wisdom, we're done, right? The model has learned the task. But look at the test accuracy. It's stuck at chance level. The model hasn't learned anything generalizable. It's just memorizing. Now watch this. We keep training, thousands more epochs, and then bam! Suddenly, out of nowhere, the test accuracy shoots up to near perfect. The model has grokked the underlying pattern. This is what we call the grokking phenomenon, and understanding why this happens reveals something profound about how neural networks actually learn.
So, what exactly is grokking? Let me break down what's happening here. First, the training loss reaches near zero very quickly. We're talking within the first few hundred epochs. The model can perfectly reproduce every training example. By traditional metrics, training is complete. But here's the bizarre part. The test accuracy stays at chance level. If you're doing a classification task with 10 classes, it's stuck at 10% accuracy. The model literally hasn't learned anything about the underlying structure of the problem. It's just memorized a lookup table. Then, after thousands, sometimes tens of thousands of additional epochs, something magical happens. The test accuracy suddenly shoots up to 95%, 98%, sometimes 99% accuracy. The model suddenly gets it. This graph shows real data from experiments on modular arithmetic tasks. The model memorizes the training data almost instantly, but understanding comes much, much later. The big mystery we're going to unpack today is why does understanding come so late, long after memorization? What's happening during those thousands of epochs where nothing seems to change?
To understand grokking, we need to think about learning as a phase transition, similar to physical phase transitions in nature. Think about water freezing into ice. As you cool water for a long time, nothing seems to change. It's still liquid. Then, at exactly 0 degrees Celsius, everything changes suddenly and completely. The molecular structure reorganizes and you get ice. Learning exhibits the same kind of discrete phase transition. During the memorization phase, the model is in one state. It's using complex, specific circuits that memorize individual examples. These work for training data but don't generalize. At the critical point, the grokking moment, the model undergoes a rapid reorganization. The internal representations restructure themselves completely. After the transition, the model is in a fundamentally different state. It's now using simple, algorithmic circuits that capture the true underlying pattern. This isn't just better performance, it's a qualitatively different solution. This helps explain why the change is so sudden and dramatic. It's not a gradual improvement, it's a phase transition where the system reorganizes itself at a critical point.
One of the most intuitive ways to understand grokking is through what I call the spline reorganization perspective. Look at this red curve. This represents how the model initially fits the data. It's complex, it's wiggly, it perfectly passes through every training point. This is memorization. The model is essentially creating a complicated lookup table that says, when I see this exact input, output this exact value. This complex solution works perfectly for the training data, but it's brittle. Any new data point that's slightly different will get a completely wrong prediction. Now look at this green dashed line. This is a simple linear function, just a straight line. It's not quite as perfect on the training points, but it captures the underlying pattern. And crucially, it generalizes perfectly to new data. Here's the key insight. Both solutions fit the training data well enough to get zero training loss. The complex solution is slightly better, but the simple solution is good enough. During those thousands of plateaued epochs, the model is gradually discovering that it doesn't need all that complexity. It's realizing, wait, I can represent this data with a much simpler function. When it finally makes that discovery, test accuracy jumps. The model hasn't learned more data. It's learned to represent the same data more simply. And simpler representations generalize better.
So what's actually driving this transition from complex to simple? Three key mechanisms are at play. First, weight decay. This is a regularization technique that penalizes large weights. Think of it as a gentle, constant pressure pushing the model towards solutions with smaller parameter values. Early on, when the model is racing to fit the training data, this pressure is overwhelmed by the need to reduce training loss. But once training loss is near zero, weight decay becomes the dominant force. It slowly, gradually pushes the model away from complex solutions towards simpler ones. Second, circuit formation. Neural networks can form different circuits, different pathways through the network that implement different algorithms. The memorization circuits form first because they're easier to find. They're like the greedy solution. But the algorithmic circuits, the ones that actually compute the underlying function, take longer to form. They require coordinating many neurons in just the right way. During grokking, you can actually watch these circuits compete. The memorization circuits gradually weaken as the algorithmic circuits strengthen. Third, implicit bias of stochastic gradient descent. SGD naturally favors low-complexity solutions, solutions that can be expressed with fewer bits of information. But here's the catch. In high-dimensional spaces, finding these simple solutions takes time. The optimization landscape is vast, and the path to simplicity is long. This is why you need to train for so long past zero training loss. You're navigating through parameter space toward the simple basin. All three of these mechanisms work together to drive the grokking transition.
Let's zoom in on what's actually happening during training. Grokking involves three distinct phases. Phase 1, comprehension, or really memorization, the model quickly finds some solution that fits the training data. Any solution will do. It's taking the path of least resistance. This happens in the first few hundred epochs. Think of it like a student cramming for a test by memorizing specific examples. Fast, but not understanding. Phase 2, this is the long, mysterious middle, the reorganization phase. On the surface, nothing is changing. Training loss is already at zero. Test accuracy is still at chance level. But internally, everything is changing. Weight decay is slowly reshaping the loss landscape. The model is exploring the flat region around its current solution. The simple solution basins are gradually becoming more attractive relative to the complex solution basins. This is like that student, weeks after the test, gradually starting to see patterns, starting to realize there's a simpler way to think about the problems. Phase 3, consolidation, the grokking moment. The model rapidly transitions from the complex solution to the simple solution. Test accuracy shoots up. This visualization shows the energy landscape. The model starts in the memorization basin, a local minimum that fits the training data but doesn't generalize. Through continued training with regularization, it escapes and rapidly descends into the generalization basin, a different minimum that represents the simple algorithmic solution. The key insight: both basins have low training loss, but only one has low test loss. Grokking is the transition between them.
So what does this mean for practitioners? How should grokking change the way we train models? First, and most importantly, train longer, much longer than you think you need to. The standard practice is to stop training when validation loss starts increasing. That's when you're overfitting, right? But grokking tells us that's not the whole story. Sometimes you need to train for thousands of epochs after you've achieved perfect training accuracy. The breakthrough may still be coming. This is especially true for tasks where you suspect there's a simple underlying algorithm, mathematical operations, symbolic reasoning, algorithmic tasks. Second, weight decay is crucial. It's not optional for grokking. It's the mechanism that creates the pressure towards simplicity.
Without weight decay or other forms of regularization, the model may never escape the memorization basin. The experiments that first discovered grokking found that removing weight decay completely prevented grokking from occurring. So tune your weight decay carefully. Too little and you won't grok, too much and training becomes unstable. Third, monitor your test performance even after training loss plateaus. Don't assume that because training loss isn't improving, nothing is happening. Set up your logging to track test metrics throughout training, even for tens of thousands of epochs. You might discover that your model suddenly gets it long after you would have normally stopped training. Finally, grokking is most dramatic on simple underlying rules. Modular arithmetic, permutation groups, simple mathematical operations. These are where you'll see the clearest examples. For more complex tasks like image recognition or language modeling, you might see grokking-like behavior, but it's more subtle. The principles still apply, but the transitions are less stark.
Let me wrap up with the key insights we've covered today. First, grokking reveals that memorization and understanding are distinct phases of learning. A model can perfectly memorize training data without understanding anything about the underlying pattern. True understanding comes later, sometimes much later. Second, models can reorganize their internal circuits from complex to simple. They don't just learn more, they learn to represent the same information more elegantly. Third, phase transitions in learning mirror physical systems. Just like water suddenly becoming ice, neural networks can suddenly transition from one type of solution to another. Fourth, training far past zero training loss can unlock generalization. The conventional wisdom says to stop when you start overfitting. Grokking says sometimes you need to keep going. Fifth, weight decay and regularization enable this transition. They create the pressure towards simplicity that drives the reorganization. I'll leave you with this thought. Sometimes the best solution takes the longest to find, not because it's complex, but because it's profoundly simple. Grokking teaches us that simplicity is hard. Finding the elegant solution takes time and pressure. But when you find it, you don't just get better performance, you get true generalization. Thank you. I'm happy to take questions about grokking, phase transitions in learning, or any of the concepts we've covered today.